So now we're going to look at non-lockable energy sources. Kinetic, anything moving. Potential from gravity, potential from springs. Also, there can be a potential from capacitors as well inside a machine. Most capacitors in modern equipment will self-discharge over a period of time. Older equipment, you really need to understand if there's a capacitor in there, how to discharge it, how to safely bring that capacitor to zero energy state. Thermal energy, how do you dissipate that? Wait for it to cool. How do you speed that up? Throw water on it? Yeah, the electrical cabinet can be cooled right down, right? Now it's safe to work on it. Put a fan on it. Cool it down quicker. If it's a component like an air handler unit, you can run cool water backwards through it to cool it back down. A lot of people need to service these things quickly. Thinking of ideas to get them down to a serviceable state quicker boosts productivity without jeopardizing safety. Oops. Hydraulic. Hydraulic can be a non-lockable as well as a lockable. If the valves are coming into the equipment, they can be locked out. Hydraulic pressure can also be retained in the equipment and have to be dissipated. So sometimes hydraulic pressure goes horizontal. In that case, it doesn't have potential energy because it can't fall, but it can bind up. And when you're servicing that, that hydraulic pressure can be released. So you need to dissipate that before you work on it. And lastly, we spoke about chemical a little bit. As a non-lockable source, anything that's inside the equipment that you can't neutralize, sometimes you just have to wear PPE to protect yourself. And that PPE will vary depending on what the severity of that chemical is. So kinetic energy, defining as moving parts, flywheels, drive shafts, fan blades. This is a good example here, large flywheel. When you shut machines down with flywheels, how long does it take them to stop? You guys have a lot of flywheels. How long can it take a flywheel to stop on a big punch press?
3 to 4 minutes.
3 to 4 minutes? I've heard of them so big and the bearings are so smooth, it'll take half a day for the flywheel to shut down. The 3 to 4 minutes probably comes from the brake engaging. If that brake malfunctions, you need to know that so that you can recognize it's still spinning. You can't hear it. Sometimes it's silent. 4 or 5 hours to dissipate kinetic energy, that seems excessive, right? It also seems like something that you wouldn't anticipate if you're working on it. You properly shut down the electrical, you attempted to restart it, it's not restarting, you get in there and start working on it, and then that kinetic energy has the power to cycle the whole machine, probably 2 or 3 more times without outside power. So a lot of potential energy in flywheels. Drive shafts. Where would the drive shafts be located that we'd be exposed to? Lathes, spindles, drive shafts. Drill presses. Think of things that are just rotating. It's not necessarily where it gets its power, it's where it uses its power now. Before, we're talking about flywheels, that's where it gets its power from. Electrical powers the flywheel up to speed and it uses that to get its energy from it. With the drive shafts, it can continue spinning after we shut it off, you just have to wait for it to stop. Fan blades, anything else? What about a table saw? Is that enough kinetic energy to note? Absolutely. A lot of injuries every year from the seemingly obvious. Don't put your hand in a moving table saw. You know, they're not all from running your hand accidentally through it. It's shutting it off, not waiting for it to stop, and thinking that you can stop that lightweight blade. Well, the blade's connected to a shaft, which is connected to a motor, which has a lot of inertial force behind it. And because of that, people underestimate it. They're surprised when they touch it and it don't stop. Elevated loads, another example, what not to do. As you can see here, he's got it properly blocked out. It looks like he's welding on his fuel tank here, so probably wearing PPE. The potential energy is defined as anything that can come down, anything that can move after you have it locked out. And potential energy sometimes needs to be locked out, or dissipated, blocked out, before you de-energize the machine, because you need that control to move the machine to the proper position. Secure with blocks or pins, and make sure it's designed to support the weight of the machine. If you're that operator in that example and you're working on a 300-ton press, is a 4x4 piece of wood going to support you? No, not if it's a 300-ton press. So you have to make sure the block's properly designed. Most modern equipment, luckily, comes with blocks that you can self-engage. and utilize the engineered-in blocks. So older equipment needs help. You need to use a block that was designed by your engineering department. Hopefully it's made of a specially designed material like steel, something consistent. What's the disadvantage of wood, even though it ideally can support up to 5 ton? Ages, right? People run over it with fork chucks, dump grease on it, gets splits. And then the theoretical maximum goes way down. I wouldn't trust it to over 500 pounds, let alone 10,000. So instead, always use a specially designed block if it's available. Until then, maybe use 2 wood blocks if it's a piece of machinery you're unsure of. I also mentioned for potential energy springs. This is a common application where you'll see that in your facilities. Overhead doors. What other potential energies does an overhead door have other than spring? Gravity. Yeah, we just talked about it. The up and down motion of the door, when it's up, it has potential energy. When it's down, it has potential energy. Springs are wound to lift the door back up to counterbalance the weight. If that's a 300-pound door, how much spring tension do you think is in those springs? 300 pounds at least to make the door light when you lift it up, so we can lift it. So when you're working on or around springs, make sure you understand the force behind them. Not always able to dissipate spring tension. Sometimes you'd have to use tools to keep your hands out of the movement of that. And I know in some manufacturing processes, the springs will stay loaded when there's a jam. So when you're getting in the machine, you've locked it out, you've done everything you can to make it at zero energy state. The only way to dissipate that spring is to use a tool to clear the jam at that point. So when it does clear, the tool gets harmed, not your finger, not your hand. And those are the ones that get you because you think you're at zero energy state, but you're really not. As long as springs are there, you have potential there for energy to be released. Example of thermal energy is an oven here. It could be on a desktop oven, could be a welding rod heating oven, could be a regular oven. There's thermal energy. Air handler unit is another good example. And you just need to wait for it to cool. That's all. Some obvious examples: boilers, heating loops, and air handler units. And some less obvious examples: air compressors and air conditioner condenser units. 2 common areas of burns. Air compressors can generate a lot of heat when they're compressing that air. The heat has to go somewhere. It gets dissipated through fins and ducts, and that actually can possess a large amount of thermal energy. Hydraulic energy. Pressurized hydraulic lines can store energy even after you have them locked out. It can cause movement if the valve's moved or if the load is removed. To verify the pressure's been removed, move the valves, check the gauges, use the machine to verify that before you work on it, that it's zero energy state. And those are just some of the non-lockable energies. There are others that are going to be in the facility.